Hi everyone, my name is Karthik, and with my partner Brian, our project was working on enabling privacy-preserving inference on the edge with ARM TrustZone. So first, the motivation. Privacy is a huge concern when you're surrounded by all these devices with a variety of sensors like cameras and microphones. And as edge devices for machine learning become more commonplace, it's really only going to get much worse. So you can imagine that if an attacker were to gain control of a device, it would really be a total breach of privacy. So the question we try to solve is how can we have privacy preserving machine learning at the edge? The real problem that we see here is with the recording of raw sensor data. So our proposed solution is to use a secure enclave to interface with the sensor, to store the raw sensor data and run the machine learning model. And then to the application that's running in the non-secure world, we only present binary output. For example, is a person detected or not detected? And this also allows us to rate limit the outputs from the secure enclave. In order to audit the data recording, we can fill up our memory with these special data values, and then at a later time when we'd like to audit the system, we could examine how many of the data values were overwritten, telling us how much memory was actually used. We implemented this system on the ARM Cortex-M33 on the Nordic NRF5340 PDK board. And we used the Google Coral camera on the Coral board and communicated a frame that we captured from the camera through UART to our Nordic board.
All right, so my name is Brian, and I'll talk about how we use ARM TrustZone in our project. And to start, TrustZone is a security extension for ARM, which divides the processor into the secure and non-secure states. We're primarily interested in the memory protection unit to isolate sensitive data, such as our image buffer, from the user application running in non-secure state. And to transition from the secure to non-secure state, we use a variant of the ARM branch instruction, but to go the other way, we used a secure gateway instruction. And we're able to protect sensitive data by partitioning both flash and RAM in trusted code. We do this by setting flash and RAM permissions at runtime. We also set the virtual table offset at runtime to ensure that each security state has its own stack and handlers. What follows below is the code snippet that we use to do this. And although setting up TrustZone is non-trivial, we abstract this away from the application programmer. Secure inference can be triggered with a single API call, as you can see here, resulting in a binarized output from the model, as well as ensuring that any attempt to load from the secure buffer will result in a fault. And it's at this time that we'd like to thank the EE292D teaching staff and affiliates for guiding us through this class, and thank you for your time.